Karthik Thakore is an entrepreneur, a founder, and an experienced AI and engineering leader in technology with a focus on healthcare. Since 2019, he served as a core contributor in producing new technologies, leveraging medical data, using data engineering, data science, and clinical modeling. And currently, he's the co-founder of Haji AI, and he's an open source maintainer. Prior to his current role, he served as a senior data engineer at Better Doctor, Human API, and head of data science at Newtopia. He received his master's in biomedical engineering and also his bachelor's of engineering from Western University in Canada. And today he'll talk to us about a VM containerized approach for scaling tinyML applications. So take it away, Karthik.
Hey, good morning, everyone. So I wanted to talk about a different set of tools that we're looking at building into the tinyML applications. And coming from the software land, and especially from doing a lot of medical applications, one of the things that we've started to see is that the type of applications that we imagine are going to be on tinyML are going to be very, very different than we think are going to be applications that are running in the cloud right now. There's been a phenomenal amount of hardware work that's been done. There's a phenomenal amount of software tooling work that's been done. But what's a little bit different about tinyML applications is the fact that we don't know how all of the different models are going to come together to work together to develop a very unique type of application. And so there are some operating theses that Haji is, thinking will happen. We feel that as more developers come on and build applications, not necessarily just models, they'll be using tinyML as anything else. They'll be using it and leveraging it in ways that we wouldn't have necessarily thought about. And one of the things that's going to become more and more critical is as more of the general populace becomes dependent on tinyML applications, service uptime, security, and privacy are going to become very, very hard requirements. Like if you can imagine now, Google Maps going out of service or Uber going out of service, those things are start to impact people's lives, and we're going to start seeing that with tinyML applications. A device going down in one small application may not make an impact to the overall tinyML application at scale. And so these are some of the theses that we wanted to start thinking about. How can we start building software tooling that would address some of these problems? And so some of the problems that we know, for example, is when you have devices out in the wild, it's not necessarily guaranteed, that models can't be downloaded and reversed, especially if they've been training on that regular data that's been coming in from that environment. We know that signed applications are going to become very, very important because we've seen that in any other computing spaces out there. Deploying stuff onto the web, what does that look like? Deploying stuff onto other data centers, what does that look like? At some point, security, privacy, and uptime is going to become critical for us to start thinking about. So what we started thinking about is, what does privacy and security first applications look like if we had all the tooling in place? We're seeing some current solutions, and one of the most critical change in the industry that's coming up is that the way data is being collected, there's so much data out there right now. And as we add more sensors, there's even more data out there. And collecting all of that into a central location to do training or even to do any sort of model inference to send out models into the tinyML devices is going to be a huge privacy and security risk. So how do we ensure that the models that are sent out are signed in a way that they're not reversible? So that means basically the devices themselves can't be exploited. And at the same time, regular updates can go out so that the service uptime and reliability of that application is upheld. And the way we think we can do this is by thinking about topologies of several sensors working together, or topologies of several devices working together to serve the tinyML application. And that's the context in which we've been thinking about building containerizations or tiny containers. And now if we were to think about even further, what a potential type of application we could see as something going from tiny to not so tiny to a city level or to a state level. At each level of these things, there's more and more data that would need to be collected for a traditional ML application. But in tinyML, what we can do is have each one of these layers have their own models running and aggregating only insights, not necessarily data. And if we wanted to serve this type of applications, containerization becomes very, very crucial. Because if you updated something at the cloud versus updated something at the city level or updated something at the thing, you want to have a consistent set of ML models that are going out there so that they can communicate with each other. So these were the topics we've been exploring, and we wanted to reimagine what those toolings would look like. And so we started to actually build together a container system. And the container system on the right, you will see is a very simple descriptive way of describing what a container or tinyML application could look like. So I'm going to show you these running in a second, but let me just walk through it. This is very similar to Docker, if you've heard of it. And basically what we have is we're able to say, hey, we want access to certain capabilities. Different devices can fulfill these capabilities in any which way they can think about. We're going to take those capabilities and we're going to send that through a normalization block. And that normalization block will then send it to a model that happens to be a TF-like model. And those can then be, the output from that model will be labeled with another post-processing block. And so when we define the final one, it's basically a ML pipeline that can be run and then send stuff out to the serial. So this is a very descriptive way of describing a container and being able to package the entire tinyML application together, not just the model. Now, there's obvious overheads with this, and I'll go over in a second, but I want to show you a few examples of how this works. So I'm just going to jump into the terminal, and one example that we have is of the person detection model. And in this one, it takes an image of size 96 by 96 of U8, and then it will turn that into, send that to the person detection model that's available on file. It'll do a post-processing block, which will label the outputs that are coming out. These are essentially just probabilities that are coming out. And then it will output that to serial. So this works right now on several different devices, and I'm going to show how we build these containers. So I'm just getting a lot of pop-ups from the WebEx. I'm trying to handle that while I'm doing this. And so the way the tooling that we built allows you to build these room files and turn them into containers. And they're around the size of going anyway from 1 kilobyte up to a couple hundred kilobytes. And we're working on containerizing them, compressing them further. And what you can do is once you've built the container, you can actually, you can actually run it directly from the command line itself, and then you can send it images. And you can also deploy these to the mobile phone. There's a video shortly that I'll show you outside. And in the future, what we're going to be doing is we're going to be making this containerization system available also for Arduino devices. We've been able to take certain tinyML applications and moving them directly to the chips. And so there's a few other examples that we have. And so another one a little bit more complex is using a FFT processing block for sound signals that are coming in and running the microspeech model that we've seen in the tinyML community quite a bit. So this one is very similar. Again, you have capability-based security built into the container itself. So every time a container asks for signal data, it can describe a capability block, and the device can decide what type and how much access that the container is given to the rest of the system. Once that sound data comes in, again, you're describing the type of data that's coming in, what is the output of that, and this descriptive way also allows you to make very quick changes. So without necessarily having to repackage everything and redeploy everything. So let me show you how that works. I'm trying to switch over here. So let's say we build the microspeech example. Profile. And what we'll do now is with the first one, we'll actually run the no, and let's say we want to change the labeling for whatever reason that is, right? So we can go back and very simply, without having to go deeper into the code, we can just change the labeling over here. Sorry, my bad. Demo gods are always a little bit finicky there. And what if you rebuild the container without necessarily changing any of the other stuff, we can actually change the label output where before it was no to n without any additional code being done. And this is an advantage for a lot of data scientists who are not necessarily familiar with hardware tooling to be able to do this in a much easier fashion. These containers right now come with a provider library that runs both on the Arduino ecosystem on iOS and Android. We're also looking at bringing the ML operations themselves to the from the VM directly to the hardware. And so this is our first release. We're going to be releasing this out in May. And what I wanted to show you guys next was this is kind of also the backup, and this is a video that's available on our website. I'm gonna mute this, and we also have this connected up to. Sorry, my bad. I didn't realize the video would take a while. So I'm just gonna skip ahead a little bit here. So what does this look like in terms of like, where is the actual trade-off? So the biggest trade-off that we've seen has been purely on the memory utilization, because what's happening with the virtualization is we're taking the entire application and putting it in bytecode, but that bytecode has to be completely unraveled and put onto the chip so that it can run as a program. And this is one of the places that we're seeing a huge increase in the amount of memory that's being used. And it's a 4x increase. This means it limits the lower end of the devices that we can go on top of. We have some plans in the future on how we can address this. The other sort of benchmark that we've been also looking at is CPU benchmark. So on the right, on the left over here, you're seeing the native benchmarks, where the average time is in nanoseconds. So this was on the Jetson Nano, and the containerization was about was an order of magnitude up in terms of microseconds. But however, one of the things that we've noticed most interestingly is that most of the computational increase over iterations has been very stable between the containerized and the native. So that basically means that as we're able to improve the performance of our VM, our virtualization environment, we will be able to avoid any exponential increases in iterations as new data comes in. So this is some very early results, and we're still working on fleshing this out, and we're going to have all of our tooling and our code released in an open source release. We are also working on benchmarking several other devices. And so our website is hotkey.ai. And if you have any emails, please reach out to me at community@hotkey.ai. Thank you very much.
I'd like to acknowledge our sponsors. First, it's ARM that develops software and hardware for tinyML. Qualcomm, Samsung, these three are the executive sponsors. And then followed by platinum sponsors, ETA Compute, Lattice Semiconductors, and the gold sponsors are BrainChip Corporation, Cisco, DSP Group, H-Impulse, EMSA Visual Sense, General Matter Labs, Greenwaves Technologies, Hymex, Imagimob, Latent AI, Maxim Integrated, Hixo, Reality AI, SenseML, Silicon Labs, Sentient, and Google TensorFlow. XMOS, and the silver sponsors are H-Cortex, HOTS, and Synsense. Again, we are very grateful for their continued support, and this is a great testimony that the foundation and this community is really of huge interest for the companies and for the whole world.